All right, let's go ahead and get started. I hope you all enjoyed your weekend. Announcements. So you'll have a new hand-in homework posted on Thursday. So no homework due this Thursday for the hand-in, but there'll be a new one. Stat lab homework, that chapter 13 is due this Friday at 11:59 p.m. And then exam 2, I decided to give a linear curve. So that means the what you got will be put through this function right there. And I picked this function so that if you got 100, you'd still keep 100. And there were 2 people that got 100 on this exam. And I also decided to do the curve because there were a higher proportion of you that got less than a 67.5 than I wanted. So to get a C in this course, you have to get a 67.5% overall. So I wanted to make sure that not too many of you had too low scores on that. Another thing about this curve is that what it does is it gives more points to people who got a lower score, but then you still get some points added even if you got like 80s, 90s, like that, just to a lesser amount. All right. Any questions with that? I have the scores up so we can see what the median and mean and all of that was. So let's just look at the original one. Oh, yeah. Oh, I'll put them up on Thursday. Yeah, so I'll give it out when you get your actual test back, and then I'll have the solutions in the exam like I did last time as well. But just in general, so here, this was the one that made me want to do the curve, was the Q1 was 60%. So that means less than about 25% of you got less than 60. But then this one's really good, this Q3 right here. So 25% of you got B's or higher. So 83 or higher. So it was it's kind of I didn't want to give just a flat curve, just give everybody like 5 points or something, because we already, some of you already did quite well on this exam. Maybe I could look at the histogram here. Yeah, let's just do both of them this time. Well, no. Let's do summary stats with both of them, so you can see. All right, so here with the curve, the max is still 100, but then this Q1 is up to the 67.5 now. So that's to get a C minus. And then the Q3 went up only a little bit from 83 to 86. And the mean went up by about 5 points. So, all right, let's look at the histograms. So there, so you can still see that. I think this will be good. All right, so this is the original. This is the original histogram. And you see most people got in the low 80s. So that was the most common score. And then about half as much in the low 90s, 200s. And then kind of dropped off from there on the left side. So yeah. So then with the curve, it looks a little more normal, like this, just a little bit. And you still have the highest amount of people in the 80s. But now these scores on the left are moved up a little bit more to make it a little nicer for you guys. All right. Any questions with that? Yeah, I think let's go into the notes now. We're doing confidence intervals. So kind of think back to we're trying to capture the true proportion is what we're trying to do. Using an interval. So say the true proportion is probably between this and that is what we're trying to do. All right, so we want to try to talk about what this means. So if we were to say we are 99% confident that this interval contains the proportion of all US adults who do not want to see Roe versus Wade overturned, what does this mean? So another way of saying this is that in repeated sampling, %99 of intervals constructed in this way will contain the true proportion of all US adults. All right, so this is on page 199. All right, so let's do a little bit of a review here. Any questions on that for starters? All right, so we need to fill in these blanks. So I forgot what it is, so let's just recalculate what this interval is. So we've got something that looks like this. So p hat plus or minus z star square root of p hat q hat over n. That's what we use to find confidence intervals. Anything? So for a 99% confidence level, we use a z star of 2.576, and that's just in a table. You can look that up. And then if you look back onto page 198, it says that p hat was, 69%. We're using a z star of 2.576. And anything else we need to know? Sample size, 1502. All right. All right. So let's just put in these numbers here. Got 0.69 plus or minus 2.576 square root of 0.69 times 0.31. That's 1 minus 0.69 right here. That's what 0.31 is. All over 1502. Okay. All right. And then if you calculate that out, see what we get. square root 0.69 times 0.31 divided by 1502. And then you do a plus now. So don't try to do both a plus and a minus at the same time. Do second enter to find that, the next one. Right. So that's from 0.659 to 0.721. Any questions with that? How I type that in? All right, cool. So yeah, you write it like this, 0.659, comma, 0.721. And this is interval notation. So what that means is that the lower bound is 0.659 and the upper bound is 0.721. So it's literally an interval like this. It's some kind of a length. 0.659 to 0.721. All right. So so here's some things not to say. So here they give this this interval right there. But the issue is that if you were to do another sample, you'd get a different p hat. And that means that you would get a different interval. So it doesn't make sense to write down this specific interval if you're talking about containing p a certain percentage of the time, because it's many different intervals depending on each of the different samples that you do. All right. Yeah, that's the underlying part. Interval will change from sample to sample. Right. And then here's another one. So there is a 99% probability that P is between 0.659 and 0.721. So this isn't really a probability. P is either in that interval or not. So the probability comes here from saying that the chances of getting an interval that contains P is this percentage, not that the P itself is in this specific interval. All right, so what's varying here is the interval to interval, from sample to sample. Not P itself. There's just one value for that. Right? Questions with that? Yeah, it's kind of a little bit of a hard concept here, but just try to remember that it's the confidence intervals that are changing depending on the sample, not P itself. There's just one value for P. All right, so we want to know will a, I think that was as good as it's going to get. All right, so will a 90% confidence interval for P be wider or narrower? So I'll ask you, what do you guys think? Wider or narrower? Narrower. Why is that? Yeah, exactly. So you're less confident with a smaller interval that you'll capture that P. And the value that will get smaller is Z star. So higher confidence levels have a bigger Z star, a critical value. And that is in the formula why it's a smaller interval. So narrower. And then here we can think back to the formula for number 5. So if we have a sample size that's 4 times as large, instead of n in the formula, we would have 4n. And then with the square root sign, that becomes a 2. Square root of 4 is 2 down there. But let me write that out. So we start with p hat plus or minus z star square root of p hat q hat over n. And then what we end up with is p hat plus or minus z star square root of p hat q hat over 4n. Right there. So this is what you start with, end with. And then we can write this in another way. P hat plus or minus z star 1 over square root of 4 times square root of p hat q hat over n. All right. So since everything's multiplied together under that square root sign, it's okay to separate it out like that. All right. And that's the same thing as p hat plus or minus 1/2 z star square root of p hat q hat over n. So this interval, how long will it be? It will be 2 times the margin of error. So, or in other words, 2 times the margin of error is equal to 2 times 1/2 z star square root of p hat q hat over n, which is just z star square root of p hat q hat over n. And then the interval up here, what you started with, was 2 times the margin of error as well. But in this case, it's actually just 2 times z star square root of p hat q hat over n. All right, so if we compare the two, we see that we went from 2 times that margin of error to just 1 times that margin of error. So the effect was that it was halved, if you actually want to check the lengths of the intervals. You could just look at this, this number here and see, oh, okay, it's a half. It's a square root of 1/4 or half. All right. Okay, so we would say, I guess to answer the question, we would say narrower by half. All right, so if we increase the confidence level, the width of the confidence interval increases. And then the other thing is if we increase the sample size, as we saw here, the width decreases. And you can tell that by the formula, by how big your margin of error is. Okay, so let's do another survey here. All right, so suppose we want to take another survey of the Roe versus Wade, see if it's changed. We want to estimate the parameter of interest to within 2 percentage points. So that's the margin of error here. And then with 99% confidence. So how large would our sample need to be? So this problem is going to require a little bit of algebra, is what's going on here. All right. So in this bullet, it says that so the margin of error is equal to 0.02. And then we're being asked to solve for n in the equation on the next page. So we're supposed to solve for n. So we can just do this and just find a general formula for what n should equal, given the margin of error in p hat and the confidence level, which gives us z star, the critical value. So let's just solve it. So I'm just rewriting it again. All over n. All right, so we want to solve for n, so let's just get z star on the other side. And if you know how to do this already, just tune me out and do it on your own page. All right. So we got the margin of error over z star equals square root of p hat q hat all over n. Now we take the square of both sides, get rid of that square root sign, because we want to end up with n equals. Square both sides. And now we want n out of the denominator, so let's just take the reciprocal of both sides. And now we want p hat q hat on the other side, so we just multiply both sides by p hat q hat q hat. So we end up with n equals p hat q hat times z star squared all over margin of error squared. And if you wanted to, you could keep track of that and use that in future questions that would ask you for what the sample size should be. Okay. So problem with this formula is, what if we don't know what p hat q hat is? So if we look back on the other page, they didn't actually give us p hat or q hat. So the problem is we don't know p hat. That's an issue. All right, so two solutions. You could guess. Or you could use the worst case scenario, would be 0.5 for p hat. Because that will give us our widest margin of error. So that'd be the worst possible guess, is 0.5. So in this last sentence, it says that using our worst case value, p hat equals 0.5, we would have a larger sample size than if we had maybe a smaller p hat. Only by a little bit. So it would translate to a 20% larger sample size if p hat is between 0.3 and 0.7. Right. All right, any questions with this? All right, so let's actually do that. We can do that on the next page here. We can perform that calculation. So n equals p hat q hat times z star squared, the margin of error squared. That's our formula. All right, so n equals 0.5 times 0.5. And then this was a 99% confidence level, 99% confidence level. So think back, it's on page 195. If you don't remember what a 99% confidence level with the Z star was. And that is 2.576 squared, because Z star is squared. And then a margin of error of 0.02 squared. All right. So let's type that in here. 0.5 squared times 2.576 squared divided by 0.02 squared. 4,147.36. We round up to be on the conservative side. So it'd be better to have a little bit more precision as opposed to less precision. So we're going to say this is about 4,148. Is about 4,148 people. Question? Oh, okay, yeah. So that was given in the statement of the problem. It said that they wanted to know P within 2 percentage points. So they didn't want to be too far off from where P is. And yeah, 2 percentage points would be pretty awesome for a poll, actually. From what I've seen, most of the ones I've seen are more like 5 percentage points or 6 percentage points, plus or minus, which, you know, that's quite a large margin of error. All right, so let's look at this. So we got 70% on number 7. Don't want to see Roe versus Wade overturned. Is this claim in agreement with the results P hat equals 0.69 of the Pew survey? That is, how likely would it be to observe a sample proportion of 69% if the legislature's claim of 70% is true? All right, so this, it'll really help if we could draw a normal distribution here. And then to find how likely, we could find a area under that curve. And then that will give us how likely this would be true. So we want to, we're assuming that the claim is true. The 70% is going to be in the middle here. But then we have to find what the central limit theorem tells us. So okay, let's look at, see if we can use the central limit theorem. Can we use the central limit theorem, the CLT? All right. So in this survey, we assume that they're using some kind of random calling or randomization. So that's okay. Also, we assume that the sample size is not larger than 10% of the population. So that's okay. And then lastly, we could check the 0.7, or what was the sample size again? So with this one, this is referring back to the original. I think it was like 1502 or something like that, right? We look. Yeah, 1502. And then we need to do 1502 times 0.3. So both of those are greater than 10. So it's okay to use the central limit theorem here. Yes. All right, so the three things the central limit theorem told us was that p hat is approximately normal, centered upon 0.7, standard deviation of square root of 0.7 times 0.3 all over n, which was 1502. Which is 0.01. Oh, yeah. Yeah, sorry about that. So that's what the central limit theorem tells us. All right. So just a reminder, this is a common mistake. It is should we use 0.7 or should we use 0.69 here? So we want to use the assumptions, the legislator's assumptions. So we're assuming he's true. We're giving him the benefit of the doubt. So we're living in his reality now. We're walking in his shoes. So we're assuming that 0.7 is what P is. And then we also use that P for to find the standard deviation. All right, now we can draw this picture. So we have, maybe zoom out a little bit. All right, so 0.7 plus, and then 0.7 plus 8 plus 0.08. All right, there we go. So those are those two. So I'm just writing what these tick marks are now. And I think we need to go one more. And then subtract this off. So we've got 0.688, 0.676, 0.665. All right. So are you all with me so far? So now we're going to be able to find how likely it is to get a 69%, somewhere around here. How likely it is to get a 69% with this 70% here. All right, so we want to decide now, should we shade to the left or should we shade to the right? That's what we want to decide. Because if we shade to the left, that would be how likely it would be to get 69% or less, or more, or less than that. So I say that we should shade to the left. All right, and now we can calculate how likely it was to get 69% or less from that. So now we use the normal CDF, lower bound of negative 10 to the 99th, upper bound is 0.69. Mean is 0.7, standard deviation was 0.00118. 0.0118. All right. And then that gives us a 19.8% chance of getting that proportion. So that's actually pretty likely. So it's not that strange to get that small of a p hat. All right. So normal CDF is here. I gotta move that. Negative 10 to the 99th to 0.69, 7, 0.0118. I don't know if you can see that. There we go. And that was equal to 0.198. All right. Any questions with that? All right, so some final comments here, and then I want to show you how you could find find the confidence intervals using your calculator. All right, a couple of comments here. So taking an SRS is so important because we have unbiased estimates, and then also because we can estimate the variability. We have unbiased estimates, and then we have the variability. So then if we didn't have this SRS, so a simple random sample, it wouldn't even make sense to talk about confidence intervals. It would be meaningless because there could be some kind of a bias in there that would just completely affect your data that you gathered. All right, so let's do an example now with one prop z int. One prop z int. So let's just do the one that we did. All right, so we go into stat. And we go to tests. Then we do one prop z int, which is down here. So one proportion, and then we're using a normal distribution, so that's what the z means. And then int is short for interval. And then the way your calculator likes this is it likes whole numbers. So x is the number of successes, or the number of people who decided or supported the Roe versus Wade was supported that, I think. Oh, who don't want to see Roe versus Wade overturned. So sometimes you have to do a little bit of work to find what that number is. And all you would do is 1502 times 0.69. And that gives you the how many. So 69% of that sample said that they didn't want Roe versus Wade overturned. And then you want to put a whole number in. Let's just try it without putting a whole number in, and you'll see what happens. One prop z int. So let's say we wanted to put 0.38 in there. Confidence level of 0.99. So it says error domain. So it's not going to work. But if we put in, let's be generous and put in a 7 there. Calculate that. And then it gives you what p hat is, and it gives you what the interval should be right there. All right, so this is a great way to check your work, or just to use. If you do use this, make sure that you type in, that you write what you put into your calculator, so that you can show your work this way. Say what calculator command you use, one prop z int, and also give the values you put in there. So x, n, confidence level, all of that. All right. So we could do like a different confidence level, say 0.999. And we'd expect this to be a wider interval than before. Right there. So yeah, it goes from 0.65 to 0.73. All right. Any questions with how to use that? All right. I think this would be a great place to end today because we made it to the end of the chapter. And we can start in with the next chapter on Wednesday. Confidence intervals for means now.